Hi everyone, my name is Mingming Guo. I'm from online core data science team from Home Depot. I will present our paper with the title Online Product Feature Recommendations with Interpretable Machine Learning. Let's start. So this is the agenda. First, I will give the introduction about our situation, the problems space, and followed by that, I will introduce some related work. Then I will formulate the problem. After that, I will propose our machine learning approach and give the performance evaluation and conclude the work in the end. So product feature recommendations are critical for online customers to purchase the right products based on the right features. So because customers rely on the right product features they see to differentiate among massive similar product options. So from this image, we can see when customer want to buy a patio dining sets, they need to compare with the two products or more products which are similar based on their features. You can see the feature recommendation on the bottom left. For example, the seating capacity. This is critical for customer to choose which one they need because customer may need seats with 4 people or 6 people. So this is a non-trivial task to recommend product features that can fit customer needs. I will introduce some related work here. So for product and feature recommendations, specifically for product recommendations, there are a lot of works there. Most of them focus on several categories. First one is alternative product recommendations. The second one is complementary product recommendations. And the last one is next item recommendation. And there are tons of works there. So I will not introduce more about that. So the second one is our focus feature recommendations. In fact, from the literature, there's very little related work there. We can find some work in other domain. For example, using product features to design marketing campaign, like the reference in 12. Interpretable machine learning. So there are two main categories in the literature. The first one is interpretable models. For example, linear regression. So it's interpretable based on its simplicity and also the decision trees. The second category is model agnostic methods like limb, like a shape. So I point the two related work in the reference. So problem formulation. So the problem we need to discover the factors and also the key features that drive the major difference between alternative products or similar products. So we formulate this problem into a price-driven supervised learning problem, because we believe the price is the most important factors that when customers choose in between similar products. So we're using this price to as a label to discover the most important features. In fact, this problem is discovered by a customer survey. So from a customer survey, we found the problem that currently the feature for similar product are not very helpful on a e-commerce site. So first I'll introduce the datasets in our approach. There are two datasets. The first one is the product feature data. In this table, we have different features and also their feature values. So for example, product weights, we can see 51.8 pounds there. And the second table is the product price data. We have the product ID, we have the price. So we need to connect those two tables to get the training data. And next one is the data preprocessing. So in fact, our inputs are raw strings. We need to extract all those different kind of features. For example, the numerical features like the product weight, it has a unit LB, and we need to apply patterns or the rows with regular expression to remove this information and extract the numerical parts so it can fit into machine learning models. So the second one is the categorical features. We need to extract like features like, for example, the commercial residential use with the value of short string like residential. So this is definitely a categorical feature, and we need to, of course, extract that. And the last one is the textual features, which means in those features, the string are pretty long, so it can describe some product usage information. So in fact, in our current stage, this is not very informative for the customers because it's too long and it's not very helpful to differentiate between the similar products using those features. So we just exclude those features. So the models we use, the algorithm we use, the first one is the linear regression. So this is the first machine learning algorithm we use because of its interpretability. Most importantly, linear regression can learn the feature impact or the feature directions, positive or negative impact to the target variable. So this is very helpful in one of our use case in the later session. Light GBM, so this is the first tree-based algorithms we use to derive feature importance. So it learns the feature importance by computing the average gain of the features in the model training process. And the last algorithm we use is cat-boost. So cat-boost is also another sophisticated tree-based algorithm. It can handle category features without the need to split those category features. So, so based on our exploration, this will give categorical features a better chance to rank higher. Then I will introduce the Shapley value. So Shapley value is a explanation method with a solid theory from game theory. So it is about how the payoff is distributed to the features in prediction task. For example, in a category named drill, we can see from the first image how the feature distributed, how the feature contributed to the final prediction. In this image, we can see the base value is the average prediction value for the whole training data, and the output value is the prediction for this specific instance. And we can see the model type with brush lists push the price higher or closer to the base value, and but the product weight push the prediction for this instance away from the base value. So from this image, we can see how each features contribute to the price, and also we give the mean value for all the Shapley value for each features. We algorithm, we can see from second graph how each features rank in the final list. So from the image, you can see product weights, model type, trunk size are the top 3 key important features for customers to differentiate the products in drill category. So performance evaluation, the baseline, we introduce a baseline named left navigation algorithm. Left navigation features are listed on the left side of a product listing page for a specific category. From the right image, we can see the refrigerator size, top capacity refers to feet wide, some important features or listed on the left side of a specific category. So customer can select them to filter out the products. So this means this list are powered by customer engagement, and we rank them based on the engagement frequencies. But there's a problem for this algorithm. There's a code start problem, because if there's no customer clicks them or choose them, so we don't know how those features rank finally. But because it's powered by customer engagement, customer behavior, so it's a strong baseline, especially for this, the category we sampled to do the validation. So this is the offline evaluation. Now we have a couple of metrics to use for offline evaluation. The first set, so the metrics is R, NDCG, procedure, and record. From this table 1, we can see overall our algorithm is perform pretty good compare with the baseline. And even some categories like drill and building dishwashers, the NDCG for the left nav algorithm is a little higher than machine learning approach. Based on our analysis, it maybe because they are well-known categories. So customers know exactly what's the most important features and can choose that from the left nav features. But overall, our machine learning approach performed better across NDCG, procedure, and record scores. And the second metric we use is coverage. So our algorithm, in fact, boosts the coverage about 45% compared with the baseline, because we only need to use the the product attributes or features and their price in a specific category to discover the most important features. So, but for the baseline, for the left navigation algorithm, they need to use customer behaviors. So this will limit their coverage, but our algorithm boosts the coverage significantly. So online A/B test, we use conversion rate as a metric to evaluate the relevancy. The conversion rate is the number of purchases divided by number of visits. So we have two use cases here. We perform a A/B test for each use case. The first one definitely is the product feature recommendation we introduced in the introduction. So our approach outperformed the baseline with a 2.1% higher conversion rate. And the second use case or A/B test is the explainable recommendation using feature message. For example, we show a message under a specific product price saying how the customer can get the specific features with a more higher price, or spend less to get less specific features. So our approach outperforms the baseline with a 3% higher conversion rate. So both A/B tests are very successful in using our machine learning approach. So the conclusion, we use the price and the label to derive the most important product features, And we leverage linear and tree models with sharp value to understand, to rank, and to recommend the most important product features. We call it key product features. And we also leverage human experts to evaluate the relevancy for our approach in offline evaluation. And our machine learning approach outperform the left navigation algorithm, which is the baseline in both offline evaluation and for 2 use cases in online A/B test. So yeah, of course, our approach can better explain the feature importance and rank the top features that matter to differentiate among alternative or similar products, and can help customers to find the right products based on our recommendations, feature recommendations. And so this is a reference. So thank you for listening to my presentation. And if you have any questions, please reach out to me through email or in the workshop session. Thank you so much. Bye-bye.